right, thank you for the introduction. As said, my name is Sebastian Esser. I'm coming from the Technical University of Munich, and I'm happy to present you my paper, which is entitled A Reference Framework Enabling Temporal Scalability of Object-Based Synchronization in BIM Level 3 Systems. So let's directly jump into that. I'm pretty sure that most of you are familiar with the so-called BIM maturity levels. So what we currently see as the state of the art is denoted as BIM Level 2. What we do there is basically that all the disciplines that are involved in a design process are work kind of independently in their software tools that are specialized for their needs. However, we enforce them to use like data models to exchange information that we can actually perform coordination tasks and to run clash detection and also to bring these different data together. What are the basic ingredients for that? In our opinion, it's about data models. So there is a well-established, for example, IFC data model, but there are also other data models which are more targeting the infrastructure sector, for example, so like Land XML or Rail ML. But there are other data models that are more used for city modeling, like City GML. However, as an addition to that, to really make this collaboration happen right now, we also see some like technical implementations of so-called common data environments. This is also something we can consider as more or less solved. So there are a couple of commercial applications, also open source applications that already enable us to manage these. However, if we are now looking a bit further or beyond what's coming next, it's still a bit fuzzy what could be meant by BIM Level 3, so just took some statements out of the literature. However, in our opinion, we can actually break it down to two basic objectives. One is about the integration and interoperability. The other thing is about version and revision control. Why version and revision control? If we look in this current practice on how we actually collaborate together, it means that everyone is like creating his or her BIM model and then we are exchanging these BIM models. However, if you are asked to actually change something in your model, you normally go back into your authoring system, you change something and then you run the export all over again. So what we end up with is just like a list of different models which kind of share similar information across all the versions, and the change is rather small. So we are producing a lot of traffic, a lot of data exchange, which is not super necessary. That's the reason why we're now looking a bit more into this version revision control. As a technical basis, we are actually using graph-based representations. We are using labeled property graphs to reflect the actual object structure that is behind a BIM model. So you can imagine it in a way that you say, all the objects are mapped to nodes and all the dependencies that occur across objects are then reflected as relationships. And we're using like a more condensed version, not really RDF graphs, but something that's more known as a property graph where we can also attach certain semantic information to both nodes and edges. What's the mission statement behind that? In our opinion, it's quite good if we can stick with the well-established data models that we see in the market. I mean, they are well adopted in a couple of software products. Of course, they are perfect, but it still is a good thing because it's kind of accepted that they're available and perform quite well, at least in some scenarios. However, we'd like to overcome the issues that are introduced by decoding and encoding serialization stuff. So most of the time, especially if you're dealing with vendor open data models, the instances are exchanged using some sort of clear text encoding. So it could be an XML file, could be something like step express, step physical file, something like that. So there are some limitations that I will show in a minute that we also like to overcome by using really graph-based structures and to negotiate and to reason on the graph structure in itself or the object network in itself. And last but not least, we also want to properly reflect the engineering knowledge that are actually captured in these instance models, so to not lose any information. I mean, there are a couple of approaches that are trying to really develop systems to have version control as well, but they are more or less a data model in itself. How can we implement that, or what's the vision here? For this, we have defined a reference architecture and a workflow. So let's start quite simple with two users, user A and user B. Both have a normal file directory service. However, in addition to that, we also state that both users have a local repository system available where we can actually store these graph representations I was shortly mentioning in the slide before, and also a dedicated area where we can actually store so-called patches. So in the first run, what could happen? Maybe user A is creating a BIM model, for example, following the IFC data model in a first version. We can actually use an add command to actually translate the file-based representation into the object-based representation as a graph. And we can also freeze the state by running a commit command, which actually produces a patch. If it's like the initial version, so nothing was available beforehand, the patch is actually labeled delta 01. So 0 is like the nothing state, so from nothing to this initial state means that we are just capturing the knowledge on how to actually instantiate the graph in the first glance. However, that's already information that we can then push or synchronize with a central hub. The hub in itself basically provides similar functionality as we are knowing from CDE platforms. However, not managing entire models anymore, but it's more about distributing the patches that are created by all the stakeholders that are connecting to the hub. On the receiving side, we define a fetch operation that can just synchronizes the patches that are available on the hub to the local repository. And in addition to that, we also define a pull operation that basically fetches the information and also applies the patch, the incoming patch. So in this case, we are just creating the initial graph. And there's also a get operation to really reproduce the file-based representation out of our graph. That's more like an intermediate solution because for long-term perspective, we actually expect that we can directly connect to the graph itself without having this intermediate step or translation to a file representation. So far, basically everything is similar to what we see in BIM Level 2. However, if we're now considering to have an updated version of the model at users A side, we can actually say, okay, let's run the add command again. So we're creating another graph inside our repository system at user A. We can again run the commit command, and then we're creating another patch that actually just contains the information on how we can get from version 1 to version 2. How we do that, that's like worth an entire paper, but in essence, we are actually using graph transformations to really abstract the changes, so the nodes and the edges that have been either removed or inserted, and also modified potentially. Again, we are then exchanging the patch to the receiving side, and on the receiving side now, we do not have to recreate the entire graph or representation, but we can simply apply the change and update the graph representation that was stored locally on user B side. And of course, user B can also run the get command again to get the updated version as a file as well if this is actually necessary. So let's quickly address the elephant in the room. Of course, those of you who are familiar with version control systems for like software development, you might say, okay, this is some sort of Git. Why is this worth a presentation at this conference? Yes, I agree that especially the conventions on how we actually name the commands are really adjusted or aligned with what Git is also doing. However, Git is not really a solution for us. Why? That's illustrated on the next slide. So let's just quickly have a look on two models. Both models are consisting just of a wall and a door, so nothing spectacular. And we could actually ask ourselves, are they similar or not? Just from a visual experience, I would say yes, they are. However, if you're now looking into the serialization structure, which is pretty small here, we can actually see that on the right side, we have started our entity numbering not with number 1, but with number 2, which basically results in the fact that the pure text-based diff, what Git is basically doing, will actually tell us, okay, everything has been removed, everything has been inserted. However, it is still like the same engineering knowledge. So all the dependencies that are modeled with these artificial pointers or with this, their entity numberings are still the same. It's still like the same object network that are represented in both files. However, we can conclude that like pure text-based comparison on the serialized forms is not really a solution for us. But if you're really arguing about the object structure that is underlying or encoded in these serialization structures, we can really make a benefit out of that. I was in the beginning briefly talking about the synchronization, scalability. So having this minimal set of like add, get, commit, push, and pull, we actually have enough to have like a flexible systems in a temporal scalability manner. So we can realize a system where you just have a few update or data exchange moments, where you say, okay, there's a domain A that just finishes their design, then they are pushing the final result, and at some point in time, another domain is just grabbing their information by pulling them into their local system. Then they are performing their tasks, and some later point in time, they are again pushing information. That's more or less what is illustrated on the left side. However, again, using the small set of commands that we are actually giving to the user, we can also have something that is more or less almost real time to say, okay, if you're really committing quickly, so really encapsulating also the small changes or freeze the small changes into patches, and then also to push them to the central hubs, you can actually react much quicker on design updates that might be caused by other domains, but you have to rely on them or have to react on them. So that's the benefit on our system. That's nothing we can actually specify in a global sense for any project, but it's really something that we see as a responsibility on the specific or individual project in itself. To quickly sum it up, in this paper we have presented a reference framework that supports object-based version control, also in interdisciplinary design settings. It basically preserves all the concepts that we know from BIM Level 2 implementations. So we still have a clear authorship. We still can actually reason about who has created which change, what impact does it have. However, we significantly enhance like the technology base there in a way that we can directly interact with the change information and not sending the full model and then to like recalculate what has changed on the receiving side. We have shown that the synchronization can be happen in a time flexible manner, and it also opens some new potentials, for example, in the direction of branching and merging, and also to interconnect interdisciplinary data sets into coordination models. So giving you the idea of, okay, we can actually join all the domain models together in coordination model. That's what we currently see already. However, if you then have an update to one of the domain models, you can directly evaluate the impact by just patching the new information onto your coordination model as well. And with that, I'd like to close my talk. Thank you for your attention, and I'm open for question. In the meantime, you can also watch a short video of our prototype, how we have implemented that. Thank you.